In our last example of a circuit that contains an op-amp, we will also let an ideal diode to be part of our circuit. So this will be a circuit with two nonlinear components, a diode and an operational amplifier. Now for the following circuit, we will try to obtain the transfer characteristics. Open, down. This minus 7 volts. Then in the feedback connection we have following one port. This one has 5 volt and this is also 1. And the saturation voltages are given to be plus and minus 10 volts. Okay. Now for this circuit, op-amp circuit, which contains an ideal diode in its feedback on port, we are asked to obtain the transfer characteristics. By transfer characteristics, we mean the in, the out curve, or the in, the out relationship. Okay. Now there could be many ways to approach this problem. Here is not so short, but a formal way to start solving the problem. Well, first of all, again we will try to express V minus and V plus in terms of input and output voltages, and once we have that, we can start our analysis. Okay. And to be able to express V minus and V plus in terms of input and output voltage, well, for V plus it's quite straightforward, but for V minus we have to be a little bit careful, because the expression now will be defined in a piecewise fashion, depending on whether or when this diode is on and when it is off, okay, or when it behaves like a short circuit and when it behaves like an open circuit. Now the conditions on open circuits or short circuits of that we also have to express in terms of input and output voltages. Okay, so therefore the first step is to express the current voltage relationship for this one port. Okay. So that's just one way of approaching the problem. Perhaps you have a better way, and then you're welcome to go with your own way. Okay, so this is just a suggestion, not the only way to attack this problem. Okay, so let's deal with this one port that appears in the feedback connection first. Okay, so let's call its voltage V of x. Okay, our nonlinear or piecewise linear one port component, and let this current be Ix plus minus 5 volt. Now this yields the following the xi curve. Ix, and So we did many examples that contain LTI resistors, idle diodes, and constant sources. And it's therefore easy to obtain the voltage-current relationship of this one port. And if you do that, this is what you obtain. Okay. This is 5, this is 0, this is also 5. So for voltages less than 5 volt, or for currents less than 5 amps, the component is, the behavior of the component is determined by this one resistor. Okay, so the slope here is 1. And then once the current passes the 5 amp border, okay, for currents higher than that, voltage no longer follows the current, but it remains fixed at 5 volts. Okay, that's where the diode becomes on, or it becomes short circuit. Okay, so Vx therefore can be expressed easily in terms of the current passing through our feedback one port. It equals Ix for currents less than 5 amps. Okay, and this is when the diode is off, and Vx is fixed at 5 volts for large enough currents when Ix is larger than 5 amps. Okay, this is when the diode is on. And let's call this our first equation, first characteristics, the relation that determines the dependence of Vx on Ix. Now, with that relationship, let's consider the following. Our circuit once again, okay, replacing that one port with just a simpler diagram for which the voltage and current relation is there as we obtained. And as for V+, since there is no current escaping into the op-amp through this wire, the voltage here equals, by simple voltage division, only 1/2 of V in. Okay, so this, and keeping that in mind, we can now work with the following simpler, at least simpler looking circuit. Okay, so hence we're able to simplify our circuit as follows. Plus minus 7 volt, 1 ohm, minus plus. We have 1/2 V in as a result of that voltage division, and in the feedback loop we have our one port now only described by this rectangle here, plus minus Vx is the voltage, and Ix is the current passing through it. That's our notation. Now, since there is no current escaping into op-amp through this wire, therefore by Ix we mean simply the current that leaves this 7 volt constant voltage supply. Okay. And here we have plus 10 volts and minus 10 volts. So that's our first relation or equation that relates Vx to Ix. Now what we want to do, as before, is we want to express V minus in terms of the output and input voltages. Likewise, we like to express V plus in terms of input and output voltage, but we already express V plus in terms of the input voltage. V plus is 1/2 V in. Okay, so let's put that down. There's nothing further that we have to do regarding V plus. So this is equation 2. Now, the more critical thing that we have to figure out is V minus, okay, in a useful way, in a useful expression. Now, V minus is, okay, we're talking about this voltage, V out plus this voltage, okay. So V out plus the voltage drop across our nonlinear feedback, Vx. Okay, so let's also give this equation a name. And as for the current here, Ix is 7 minus V minus, so this voltage drop across terms of 1 ohm resistor, okay, divided by 1. Okay, 1. That's our equation 4. Okay. Now what we have is, we have V minus, not only in terms of V out, we also have Vx. So we have to somehow remove that Vx dependence and obtain an expression entirely in terms of V out. And Vx depends on Ix, and that Ix depends back on V minus, okay? So therefore, removing from the picture Vx and Ix somehow, we will obtain a relation only in terms of V minus and V out, okay? And that's what we want. We want V minus in terms of V out. So let's do that. Using 1, 3, and 4, we can write the following. V minus equals, okay, V out plus Vx, and Vx is this, okay. So if you add V out both sides, we have V out plus Vx equals V out plus Ix for Ix less than or equal to 5, okay, and V out plus 5 for Ix greater than 5. So V minus therefore equals V out plus Ix, and Ix is 7 minus V minus, 7 minus V minus, for Ix less than or equal to 5. Ix is 7 minus V minus, 7 minus V minus less than or equal to 5. Okay, and then V minus equals V out plus Vx, so V out plus 5 when Ix is larger than 5. V minus equals V out plus 5 for Ix greater than 5. Ix is 7 minus V minus, okay, greater than 5. Okay. Now that this expression is something that's better than all those collection of expressions because it's only in terms of V minus and V out. But still it's not the final expression because we want V minus on the left hand side and the right hand side we want only in terms of V out. But we have some V minuses that we have to take care of. So let's take care of those V minuses. So V minus equals, suppose V minus equals this expression. V out plus 7 minus V minus, okay. Collecting V minus on the left hand side, we can write V minus equals 1/2 V out plus 7, okay. So that what this expression tells us. Also, we have to translate this into an expression in terms of V out. So let's do that. So this is valid under 7 minus V minus less than or equal to 5. Therefore, 7 minus this guy here, 1/2 V out plus 7 less than or equal to 5, and that means V out is greater than or equal to minus 3 volts. Okay, so therefore we have cleared the ambiguity with the first expression on top. So we have now V minus in terms of V out under the condition which also is entirely in terms of V out. Now deal with this bottom expression, and V minus equals V out plus 5. Okay, under 7 minus V minus greater than 5, under 7 minus V minus greater than 5, so that means 7 minus V minus is here, V out plus 5 greater than 5. Okay, and that means V out less than minus 3. Okay. Therefore, after a little bit of work, we have obtained what we aimed for. That is an expression for V minus in terms of the output voltage only. V minus equals 1/2 V out plus 7, provided that V out is larger than minus 3 volts. For V out greater than or equal to minus 3. Okay. And V out plus 5 is what V minus is under condition V out less than minus 3. For V out less than minus 3. And let's call this equation 5. So we have now what we need. We have V plus in terms of input and output voltages, but in this case it's only in terms of input voltage, and we have V minus in terms of input and output voltages, and in this case it's only in terms of the output. Okay. And now we can begin our region by region analysis. That's V plus, okay, 1/2 V in, and here we have V minus in the region. Okay, where we have V plus equals V minus, and V out is between minus 10 and plus 10 volts. Okay, now equating V plus V minus gives us the relation between input and output. Okay, 2 and 5 implies 1/2 V in, which is V plus, equals V minus, because we are in a linear region, and V minus equals that in terms of the output. 1/2 V out plus 7, 4. Now, for this relation to hold, we have a condition on V out. V out should be larger than minus 3. We also have another condition on V out. It should be in this range because we're considering the case where the op amp is in a linear region. Therefore, for this to hold, V out must lie in the intersection of those two constraints. V out within minus 10 interval and V out larger than minus 3. Therefore, the intersection is minus 3 greater than or equal to V out and less than or equal to 10 volts. Okay. And we have V out plus 5 as long as V out satisfies this constraint and this constraint. Therefore, minus 10 less than or equal to V out less than or equal to minus 3. Okay. Therefore, we have 1/2 V in equals 1/2 V out plus 7, from which we have V out equals V in minus 7. Okay. So this, the first line gives us V out in terms of V. We also have to now translate this into a constraint in terms of the input voltage, which is easy. All you have to do is take this guy and put it here. Okay. when minus 3 less than or equal to V out, which is V in minus 7 less than or equal to 10. Therefore, we have to have V in between 4 and 17 volts, so that V out equals V in minus 7. Okay, and now let's also deal with the second line. 1/2 V in equals V out plus 5, from which we have V out equals 1/2 V in minus 5. Okay, so that's the input-output relationship. And this, under which condition on V in this holds, all you have to do is take this expression for V out and put it here into the constraint. Okay, when minus 10 less than or equal to V out, which is 1/2 V in minus 5 less than or equal to minus 3. And that translates or simplified into minus 10 less than or equal to V in less than 4. Okay. So in linear region, there are two operating modes depending on whether diode is on or off. When the input voltage is in this range, the output voltage has the following relation to input voltage. And when the input voltage is in this range, the relation is here. Okay, now let's move on to positive side. Okay. Note that for positive side, we have V out equals 10 volts. Therefore, this condition holds. That means V minus equals this. Okay. And for negative side, V out is minus 10. Therefore, this condition holds. And V minus, therefore, equals V out plus 5. Of course, for negative side, V out is minus 10. Therefore, V minus is 5. Minus 5. And for positive side, V minus is 1/2 times 10 plus 7. So 17 over 2. Okay. Okay. Positive saturation. We have V plus greater than V minus and V out fixed at 10 volts. Since V out is fixed at 10 volts, equation 5, which is an expression of V minus in terms of V out, dictates that V minus equals 1/2 V out plus 7, which is 17 over 2 volts. Okay. Then equation 2, which was V plus equals 1/2 V in, says that 1/2 V in, which is V plus, must be greater than V minus, and V minus is fixed, 17 over 2, and V in must be greater than 17 volts, so that the op-amp is in positive saturation region. As for negative saturation region, we have V plus less than V minus, and V out equals fixed at minus 10 volts. So again, 5 yields V minus equals the second expression, that is V0 plus 5. V0 is minus 10 because you're at negative saturation, plus 5, that yields minus 5 volts. Okay, and then 2 once again implies 1/2 V in, which is V plus, less than V minus, which is minus 5. Implies that V in less than minus 10 volts. Okay, so when V in is less than minus 10, op-amp is in negative saturation region. When V in is greater than 17, op-amp is in positive saturation region. And in linear region, we have two sub-regions. When V in is in this range, V out is related to V in through this expression, and when V in is in this range, the relation is here. Okay. Now let's put everything into a single graph. So when V in is larger than 17, we're at positive saturation region. When V in is less than -10, we're at negative saturation region. And between -10 and 17, the op-amp is in linear region. Okay. So between -10 and 4, the slope is 1/2. Okay. Let's say, and between 4 and 17, the slope is 1. So here we have a breakpoint in the middle of the linear region. The corresponding point is -3. Okay. The slope is 1/2, and here the slope is 1. And that's the input voltage, output voltage characteristics of the circuit, which had a piecewise linear component in its feedback loop. Okay. Now, so far, we worked only with the infinite gain ideal op-amp model. Okay. And now let's justify, in some sense, that working with that model is okay, in the sense that if you work with a more realistic model, the answer that you will get will not be much different than the answer that you would have gotten with the ideal model. Okay. So let's spend a few minutes to convince ourselves that working with the ideal model makes sense. Okay. So let's consider a more realistic model of the operational amplifier. We have the following finite gain as opposed to infinite gain op-amp model in linear region. This is V plus, this is V minus, non-inverting input, and the inverting input terminals. According to our model, they're connected by a very large resistor. That's the input resistance of the op-amp. In our ideal model, we take this to be open circuit. We take it to be infinity. Then on the output end, we have this dependent source, which produces a voltage that's proportional to the difference between these two nodes, or the voltage drop across R in. and the proportionality constant or the gain is very large. And in our ideal model, we take A to infinity, but now with the more realistic model, it's something finite. And we also have some output resistance, okay, which we denote by R. And this is the output of the out. Now, let's obtain the transfer characteristics for the buffer or the voltage follower. This time, we already had that characteristics with the ideal model. Now, this time, let's work with this more realistic model. Okay. Example. Analyze the voltage follower circuit. Or the buffer. Using more realistic finite gain model. Gain model. Okay. So this is how the circuit looks like. This is V out. Here we have some load resistance minus plus. This is the negative feedback connection. And here we have the input voltage. Okay. Vs, and let this be perhaps the internal resistance of the source Rs. This current here is I minus, and this current here is I plus. In our ideal model, because here we have open circuit, those two currents were automatically zero. But now, when we use the more realistic model, they will be something non-zero. Okay, now this thing here is what's inside the op-amp, okay, what's inside the triangle. Therefore, let's decompose this thing or enlarge this thing, op-amp, using the finite gain model and obtain the following circuit. So this yields plus minus yes, and we have Rs, and we have V plus, and we have Rin. Here we have V minus, and here we have our negative feedback connection, and here we have the output node. This is RL. This is V out. This is out. And here we have plus minus A times V plus minus V minus. Okay. Now let's work with the following parameter values. A is 100,000, Rs 1 kilo ohms, Rin 100 kilo ohms, which we take infinity with our ideal model. Ro, the output resistance, is 100 ohms, and RL is 10 kilo ohms. Okay. So, with the ideal model, we obtained the following. If you recall that. Using the ideal model, finite gain ideal model, we have earlier obtained VR over Vs exactly equals 1 under the assumption that I plus equals I minus equals 0, which follow from the assumption that input resistance is infinity in our item 1. Now let's check how close we get to this idealization with a more realistic model under this parameter, this set of parameter values. Okay. So this is a circuit. Now we will study. What we will obtain is, we will try to obtain the relation between output voltage and input voltage. And input voltage now we're represented by Vs. So write KCL at the output node. So what we have is V out minus A V plus minus V minus over RO. Okay, so we're talking about this current. And now this, so we out, this node is connected to nothing, or whatever it's connected to, we're represented by RL. Okay, so by writing KCL, we're going to sum up these three currents and equate it to 0. Plus V out over RL, this current, and finally we have that current, which is V out minus Vs divided by the resistance in between, which is Rs plus Rn. V out minus Vs over Rs plus Rn, and by KCL, the sum must equal 0. Also, V plus minus V minus equals the voltage drop here equals Vs minus V out, and then for that difference of voltages, you can apply the voltage division, and this is what we have: Rin divided by Rin plus Rs times the voltage difference between this node here and that node over there, which is Vs minus V out. Now, if you replace V plus minus V minus here with this expression, this is what we have. 1 over R0 V out minus AR in Vs minus V out R in plus Rs plus V out over RL plus V out minus Vs over the resistance in between Rs plus Rn. And this equals 0. And then from this expression, which is only in terms of V out and Vs, we can obtain the ratio of V out to Vs. Let's do that. That expression over there, simplified, yields the following ratio. A R in, R out, R in plus Rs plus 1 over Rs plus R. So that's our numerator. And for the denominator we have A R in over R0 R in plus Rs plus 1 over RS plus R in. The same thing here, plus 1 over R0 plus 1 over RL. Okay. Now, with the parameter values that were given, this ratio turns out to be, so this is about 1000, and this is about 1 over 100, 0.1, 0.1, and this equals 0.999898. Okay, something clearly very, very close to 1. Okay. In fact, for all practical purposes, we can take this to equal 1. So therefore, at least for the L over Vs ratio point of view, our ideal model works excellently, okay, because the actual answer and the ideal answer are very, very close to one another. And as for the current passing through the input resistance, which formally we took to equal 0, in this case is different than 0. Let's see but how close it is to 0. Vs minus V0 over Rs plus Rin. So that we can write as 1 minus V0 over Vs times Vs Rs plus Rin. Okay, and for Vs about 10 volts, let's say, we have the current entering to op-amp from the input terminal is 1.01 times 10 to the minus 9 amps. Okay, so it's about 1 nanoamp, which again, for most applications, can be taken to equal 0. Okay, therefore the conclusion is the infinite gain op-amp model works pretty well. Model works well. In fact, it's a little bit humble statement. In fact, it works excellently. Okay, as is clear from those numerical results. Okay, before we close our chapter on the operational amplifiers, let us briefly talk about some other practical aspect of the operational amplifier, which may be useful when you're actually using operational amplifiers for some physical circuit for, let's say, your design courses, 493 or 494 in your senior year. And what we're going to talk about now is the so-called common mode rejection ratio. So let's see what that means. Common mode rejection ratio for an op-amp. Okay, the abbreviation is CMRR. Okay, so this is our operational amplifier, plus minus. This is V out. Here we have V plus, and here we have V minus. Now with our finite gain model, the output voltage we set equals some very high gain times the difference between those two voltages, V plus and V minus, provided that the op-amp is in a linear region. Okay. The output voltage for the actual physical op-amp is a little bit different than what we have taken so far. That is, V out equals not some gain times difference, V plus minus V minus, but it looks a little bit more complicated. A plus times V plus minus A minus times B minus. Okay. Now, up to now, we've taken these two gains, A plus and A minus, as a single gain, or we took them as same, and we just used the letter A to denote them. But in real life, they're a little bit different from one another. You've taken A plus equals A minus, and we denoted that gain by A. But A plus and A minus are not exactly equal in general, in reality. And how close they are to one another determines how, let's say, high quality your operational amplifier is. And the characterization of that quality is expressed in terms of the so-called common mode rejection ratio, which we will now define. Now, one implies that V out can be written as some constant AD times the difference of the voltages plus another constant times the average of the voltages. V plus plus V minus over 2. So this is called the differential voltage. And this average is called the common mode. Voltage, okay, during operation. And these two constants, AD and AC, they are defined as follows. Where AD is defined as A plus plus A minus over 2, and it's called the differential gain. Okay, and the other constant is defined as the difference between A plus minus A minus. This is called common mode gain. Okay. In our previous models, this was 0 because we took A plus and A minus to be the same, and this was simply A. Okay, the capital A. Up to now, we've taken in our finite models AC equals 0. Okay. Now here is a parameter that determines the quality, in a sense, of the op-amp, and its common mode rejection ratio, the title of our mini chapter. And common mode rejection ratio is defined as the magnitude of this ratio, AD to AC, AD to AC. Okay. Or common mode rejection ratio in dB, in decibels, is 20 log of the same ratio, okay, AD over AC. Now, it's obvious that the higher the common mode rejection ratio, the more the closer the device gets to the ideal model. Okay? Therefore, the higher the common mode rejection ratio, the better it is. Okay. Now, of course, you cannot work with a very high common mode rejection ratio. Well, for some applications you may, but because higher it gets, usually the device gets more and more expensive. So we have to figure out what's the least common mode rejection ratio that's good for your application. Okay, and for most applications, larger than 70 decibel works pretty fine. Okay. Generally, common mode rejection ratio greater than 70 decibels works fine for most applications. So in a sense, if common mode rejection ratio is larger than 70 decibels, okay, so the device is close to, for your application, the ideal model that we have been using. Okay, and widely used op-amp chip 741 has a common mode rejection ratio of about 90 decibels. Okay, so that's just a practical side information which may someday be useful to some of you.